The objectives of this paper are to present a method of detecting elephant flows in an IP network so that intelligent networks can reroute elephant and mice flows to reduce the possibility of congestion and hence reduce the risk of packet loss, which in turn will reduce the latency in the network. Although there are many other methods that can achieve this, our solution can easily classify an elephant flow within 200 milliseconds using machine learning methods, which is twice as fast as other methods available. Looking at the results table, we can see that we can achieve an F measure of 0.91 within 200 milliseconds. The closest method is based on the Hofting tree, but this takes 500 milliseconds. Although other works shown here are machine learning based, ours makes use of neural networks through LSTMs. An IP network consists of many different protocols, and TCP is mainly used for OTT streaming. This generally consists of temporally long flows that have high data rates and can easily fill network switch buffers, especially if the egress link is heavily subscribed. Although we are mainly concerned with the OTT streaming, our solution makes no assessment of the payload and treats all IP packets equally, as we use the data rate and temporal position as our sources of data for each flow. By classifying the flows early, we can signal to the network controller when an elephant flow is formed, which in turn will allow the network controller to reroute the flow, thus reducing the risk of oversubscribing the link. Generally speaking, an IP network consists of 80% mice flows and 20% elephant flows. But the elephant flows make up 80% of the total data within the network, and the mice flows make up 20%. It is possible to manually reroute flows by programming the switches directly, but this is not practical in real-world applications, as each IP source and destination address, as well as each TCP port source and destination number, would need to be programmed directly into the network switches and routers. This would also heavily limit the network resilience, as auto-rerouting would not be possible. The diagram on the right shows what can happen to an OTT stream if IP packets are lost or arrive too late to be decoded. OTT uses compressed video and audio, therefore delayed packets can have a disproportionate effect on the images. Although this can be rectified by increasing the size of the video and audio decoder, the latency introduced becomes disproportionate and often too large for practical applications. This slide shows how intelligent routing in a network can reduce link congestion, packet loss, and therefore latency. On the left, two servers, server 0 and server 1, are generating mice and elephant flows respectively. It is possible that the buffer in the top of rack 0 switch could overflow, resulting in congestion in the link to the core 0 switch. On the right, the diagram shows how the elephant flow from server 1 has been rerouted so that it reaches the destination via core switch 1. But for this to be effective, the network must detect the elephant flow very quickly so that routing can occur quickly and therefore reduce the risk of congestion and packet loss. The intelligent network is effectively load balancing the flows, something that cannot be achieved automatically using standard network routing protocols. We are generally interested in classifying the heavy-hitting elephant flows, so we assume a flow is an elephant if it has an average data rate higher than 5 megabits per second and occurs for longer than 5 seconds. It is possible for mice flows to have a data rate of 5 megabits per second, but be only a few seconds long. In this case, we do not classify this as an elephant flow, as it is relatively short-lived, and it is the long flows that run the risk of overflowing the network switch buffers. If we didn't need this constraint, then classification would be easy, as we could say all flows longer than a few seconds are elephant flows, but this would lead to poor routing and would not reliably solve the problem of link congestion. Our nuance is that we can classify an elephant flow within only 200 milliseconds of continuous data from the beginning of the flow, twice as fast as other methods. In summary, elephant and mice flows can negatively impact each other due to packet loss caused by buffer overload in network switches. Intelligent networks often employing software-defined network methods can route elephant flows across different links and switches to reduce the risk of congestion. Our method is twice as fast as other methods and can signal to the network controller within 200 milliseconds that an elephant flow has been detected. And the rapid detection of the elephant flow allows the network controller to reduce the risk of packet loss, which reduces the congestion and therefore reduces latency. Our solution uses an ensemble of LSTMs connected to an MDN, which provides a binary classifier. This is the elephant or mice flow which can be sent to the network controller. From the image on the left, we can see that there are distinct patterns within the TCP flows, and by using neural network machine learning methods, we can train our model to detect the elephant flows reliably. We will now discuss each of these elements of our models. Two representative datasets were chosen and recorded from ISPs as key PCAP files over a 24-hour period. The models were trained and tested on each dataset independently of each other so that we could validate our model, but each dataset was pre-processed identically. First, the PCAP files were parsed to extract the TCP flows. Then, using the time samples, each flow was aggregated over consecutive 10 millisecond samples and partitioned into 10 millisecond time bins. Using the elephant flow rule of 5 megabits per second greater than 5 seconds, each flow was classified using a binary flag as either an elephant flow or a mice flow. As the data was heavily skewed to mice flows, we decided to randomly subsample a number of mice flows so that they balanced the number of elephant flows. Otherwise, an 80% success rate could easily be achieved just by assuming all flows were mice. The method of aggregating the data rates at 10 millisecond intervals for each flow and then creating 10 millisecond bins is a method of tokenization. We chose this so that some temporal information from the initial flow could be maintained. This also helped with generalizing the model, as the timestamps were averaged. Also, the data was sparse, and by tokenizing each flow into the 10 millisecond bins, we removed some of this sparsity. Our model is a neural network consisting of long short-term memory networks. These are neural networks that are particularly good at learning patterns within sequential data. As each of our TCP flows are essentially time series data, the LSTMs lend themselves well to this application. We experimented with different configurations of LSTMs, and from the results table, we can see that the F measure improved with the number of time bins that were fed into a single LSTM. We then discovered that if we use parallel STMs with different sequence length sizes, then the F measure further improved. We found that by applying each TCP flow sequentially to multiple LSTMs in parallel with different sizes, then our F measure again improved. We found that by using 4 LSTMs in parallel with 4 different sizes, then we achieved an F measure of 0.72 from the CAIDA dataset within 200 milliseconds during our initial research. The sequence length of each LSTM refers to the number of bins processed by each LSTM. Essentially, the ensemble LSTM with its different sizes was detecting different patterns within the TCP flows. The outputs of the LSTMs needed to be joined, and the best method we found for this was to concatenate each of the outputs into a single 128-byte sample. We did try feeding this directly into further feed-forward neural networks with some success, but we had even better results when we introduced the mixture density network, that is the MDN. At this point, we could have reduced the 128 sample directly to a binary classifier, but by feeding the concatenated 128 sample into the MDN provided a much richer source of data for the MDN. The MDN is a feed-forward neural network that consists of a series of probability distributions to provide a measure of uncertainty. We fed the concatenated output of the LSTMs into the MDN and then used this to determine whether the sample was an elephant or mice flow, with a classifier described in the next section. We can see this from the diagram on the right, where the conditional probability is formed based on the input. The MDN provides three measures: the average, the variance, and the coefficient weight of each of the MDN components. The MDN components can be thought of clusters of data points. These values were assessed, and the component with the highest value was deemed the most likely measure of the TCP flow. We then determined that if the value was greater than 50%, then it was an elephant flow, and this formed the signal that was sent to the network controller. In this results table, we can see that the F measure improves from 0.85 to 0.91 by employing this technique. Each of the pre-processed CAIDA and MAWI datasets were partitioned with a ratio of 90 to 10, where 90% of the data was used for training and the remaining 10% was used for testing. The testing data had never been seen by the model. A key part of this design involved training all of the LSTMs and MDNs simultaneously using backpropagation. Normally the models would be trained in isolation, but we found that training all of the models as a complete sequence gave more reliable results. A binary cross-entropy function, loss function, was used during training by comparing the feed-forward output of the entire model to the ground truth of the training set. The loss value was then used to determine the gradient descent value for the backwards propagation to update the weights and biases within the neural networks that formed the LSTMs and the MDN. The binary outputs of the inference were compared to the ground truth labels, and then a confusion matrix was formed which allowed us to evaluate the success of the trained models. We used the standard F measure to determine the accuracy of the model so it could be compared to other methods. But we also introduced the Matthews correlation coefficient, as this includes the true negative value in the calculation. From the graph we can see that our model, the Hofting tree and the naive Bayes methods all improve with the amount of time sequence data presented to them. However, key to success of this solution is classifying the elephant flow in the shortest time possible. Waiting for 2 or 3 seconds would not deliver the required latency performance. This diagram shows a solution that may work in a real-world example where a server is used to detect the elephant flows and signal this back to the intelligent network controller. Using GPUs, the inference time is negligible and can provide a classification signal to the neural network controller within a few milliseconds. We have demonstrated the model can classify elephant flows in 200 milliseconds on 2 representative datasets, which leads to a reduced risk of packet loss and hence latency. Our future research will reduce the tokenization data bins from 10 milliseconds to 1 millisecond and also develop a regression method so that we can predict the length of a flow based on the first few hundred milliseconds of data. Further research will investigate continuous learning so that the model can be reliably updated as the dynamics of IP networks develop in real-world applications.